Assalamualaikum and hi everyone. We are from Group 4. We will be presenting topic 3 separate by 3 parts. Part A, procurement and intermodal versus multimodal. Part B, port technology, and the last part C, ship technology. Before we begin, let us introduce our members. First, Haziq. Second, me, Alia. Third, Wan. Fourth, Noji. Fifth, Sufia. The maritime cluster drives global trade through port, ship operation, and shipbuilding. It is supported by logistics, communication, transportation, and risk management, while economics, oil and gas, consultancy, and education strengthen sustainability. Additional services like survey, catering, and multimodal logistics complete the value chain. Altogether, it is the backbone of worldwide connectivity. This picture shows all major ports in Malaysia across Peninsula and East Malaysia vital for trade and logistics. The port logistic chain connects ship to consumer through automation and smart management, from traffic control and core cranes to automate resale, warehouse, and predictive maintenance. Every step is optimized. Finally, data-driven transport planning ensure efficient delivery. Together, operation, energy management, and sustainability make port the backbone of global trade. Procurement is acquiring goods and services for external sources. Its goals are cost saving, quality, timelines, and risk control. It includes direct procurement for raw material, indirect procurement like office supply, and services procurement such as consulting. Overall, procurement ensures smooth operation, efficient, and competitiveness. The procurement process begins with need assessment, followed by market research, supply selection, and contract negotiation. Next are purchase order, delivery, and inspection, and finally payment and record keeping. Key strategy include single versus multiple sourcing, local versus global sourcing, lean procurement, and ensure ethical and sustainable sourcing. Main challenges involve supply chain distribution, quality control issue, and regulatory compliance. Altogether, procurement ensure efficient, ethical, and competitive resource management. Intermodal and multimodal are two shipment methods. Intermodal use separate contract for each carrier, allowing flexible negotiation and lower insurance costs, but it's slower and harder to track. Multimodal use a single contract for the entire journey, making tracking easier and operation faster. Both is face legal limit and frequent inspection. Choosing between them depend on logistic need, cost prioritize, and desired control.
So right now I will be presenting the part B of this topic 3, which is about port technology. So these models of a harbor demonstrates how ports are designed with docks, ships, and surrounding facilities. It helps us visualize the complexity of port infrastructures and highlights the importance of planning and technology in maritime operations. Well, speaking of the cargo, let's talk about how it's measured globally. TEU stands for 20-foot equivalent unit, the standard measures for containers. It helps ports and shipping companies calculate cargo capacities. So large ships today can carry over 14,000 TEUs, showing the scales of global trades. Those containers don't just stay in one place, they travel worldwide. So let's see the routes. So this is the map shows Yang Ming's global shipping routes. Over 80% of international trades is carried out by seas, and Taiwan's economies relies heavily on maritime transports. So these routes connect major ports worldwide, forming a network that keeps global commerce moving. Well, to understand how the ships operate on these routes, let's look at the structures of a container ships. This diagram here explains the main parts of a container ship, such as the rudders, propellers, and anchors. Well, each part plays a role in navigation and safety. Understanding these components help us appreciate the engineering behind modern shipping vessels. So now let's focus on the containers themselves. Ports use different types of containers depending on the cargo. For example, dry cargo containers for general goods, river containers for refrigerated items, and tank containers for liquids. Technology like IoT sensors help monitor conditions inside these containers during transport. So how do these containers actually move from one place to another? So let's see the processes. This slide over here shows the journey of a container, starting with road transportation, loading onto ships, tracking invoices, and finally land transports at the destination. So digital systems like GPS and electronic tracking make this process faster and more reliable. And of course, moving containers requires heavy machinery. So let's look at the lifting equipment used in ports. Ports use specialized lifting machines to move heavy containers. Gantry cranes, straddles, carriers, and lift stackers are designed to handle large loads safely. With automations and AI, this machine now works more efficiently, reducing costs and speeding up port operation. Now, let's talk about the port technology evolutions. In the past, collaboration was limited to just a few key players: port authorities, ship operators, and terminal operators. But today, the landscape is much more dynamic. We now see cargo and logistic companies, storage providers, rail and barge operators, trucking companies, and even sensor providers working together. This shift to data-driven collaboration is transforming how ports operate, making them smarter, faster, and more connected than ever before. Now let's look at the major innovation areas shaping modern ports. Our focus is on three pillars: green ports, where sustainability is front and center; smart ports, leveraging technologies like smart container sensors, drones, and big data to optimize operations; and blockchain, which brings transparency and security to logistics and cargo tracking. These innovations are just buzzwords. They are redefining how ports functions in the digital age. Green ports are leading the charge in environmental responsibility. In California, over 100 trucks now run on ultra-low NOx engines, cutting emissions significantly. On the west coast of North America, LNG bunkering is now a reality thanks to partnerships in Vancouver. European cruise terminals are investing in shore powers, and in Japan, hydrogen-powered tugboats are being launched. This example shows how ports worldwide are embracing clean energy and sustainable practice. Smart ports benefits. Smart ports brings a host of benefits. They improve logistics with intelligent rail sensors and smart parking systems. They harness renewable shore power to reduce emissions, and the sensor technology combined with data analytics boosts efficiency across the board. Ultimately, smart ports support sustainable growth, protect the environment, and deliver maximum value to customers and communities. Let's dive into a real-world examples. The Hamburg Port Authority. The smart port logistics strategy integrates economic and ecological goals across traffic flows, infrastructures, and goods movements. An intermodal port traffic center connects sea, rails, and roads, while intelligent networking ensures smooth transports. They also promote green mobility and energy efficiency, making Hamburg a model for digital and sustainable port operations. Hamburg's digital transformation includes powerful tools like first here is real-time navigation helps drivers with traffic, parking, and bridge updates. Second, shore powers from renewable supplies cruise ships with clean electricity. Third, intelligent railway points use sensors to detect wear and scheduled maintenance, which minimizing downtime and boosting reliability. Fourth, a mobile or purpose sensor tracks assets and environmental data. Five, a smart maintenance use mobile devices to monitor infrastructures and streamline repairs. And the last one, not the last one, and the sixth is a virtual depots reduce empty truck trips by coordinating containers returns, which saving fuels and cutting emissions. And finally, here we have four more digital breakthroughs. The seventh one is Port Monitor, centralized data for stakeholders from vessels position to bridge specs. And eight, e-mobility initiative are expanding electric transport and charging infrastructures. Nine, smart parking, which helps truckers find and reserve space efficiently. And the last one, 10th, the renewables energy, which efforts explore wind, solar, and bioenergy, making Hamburg a pioneer in clean port energy. Smart containers. Smart containers are revolutionizing cargo trackings. They communicate location via relay antennas, allowing partners to prepare for arrivals. Solutions like TrapSense includes embedded sensors and wireless interface, enabling real-time monitoring. With cellular network and open protocols, these containers offer global visibility and seamless integration with third-party platforms.
Next, smart containers are equipped with devices conveniently attached to assets such as dry and reefer containers, wagons, and trailers. This device capture and transmit real-time data globally. The data is aggregated through an IoT platform and transformed into actionable insights for time-sensitive decisions. Through the Traction Cloud platform, IoT data from road, rail, sea, and reefer containers flow into a central hub. APIs distribute this data to the dashboard, legacy system, and fleet management tools. A smart rules engine ensures fine-tuned data segregation and controls. Aquatic drones are autonomous surface vessels equipped with sensors. They operate without onboard personnel, supporting safe and sustainable marine operations. Applications include port inspection, infrastructure survey, water quality assessment, and environmental monitoring. The drone reduce operational costs and improve safety. They enable predictive maintenance and support sustainable practice. The workflow includes mission planning, autonomous deployment, real-time monitoring, and data analysis for maintenance recommendation. They represent the future of intelligent maritime operations. The data science team blends logistics, cargo, and transportation expertise with AI and machine learning. This helps clients predict outcomes more accurately, supporting smarter decision-making with reduced risk. They collect, cleanse, and analyze real-time data from traction device and external smart device. By integrating multiple data streams, they enable holistic analysis. This provides meaningful supply chain information and better context for collaboration with partners. The platform transforms data into actionable information and delivers it to the right stakeholder at the right time. Accessible via API, it supports time-sensitive, data-backed decision with end-to-end visibility. Partnership is central to the strategy. By sharing data, stakeholders can connect to and create real value for the customer through the collaboration. The big data workflow has 5 steps. First, data collection and enrichment. Second, ensuring data quality and integrity. Third, applying industry expertise. Fourth, offering AI as a service. And finally, enabling decision with less risk. They monitor 5 key data type, which is geolocation data, geofencing and predictive ETA, shock detection, data opening events, and also temperature and humidity fluctuation. Blockchain technology enables rights to be transferred securely between parties. It's a distributed database stored across multiple nodes with no central control. Transactions are recorded only with full network consensus, ensuring trust and transparency. This is the example of how blockchain works.
Blockchain technology is applied in both to enable secure and transparent and data sharing among stakeholders, improving efficiency and trust in port logistic operation. In this slide, I'll be talking about the ship technology. This slide focuses on ship technology, highlighting modern systems that improve vessel efficiency, reduce emission, and meet international maritime regulation. In this slide is about ballast-free ship. Ballast-free ships operate without ballast water, preventing the spread of harmful organisms and eliminating the need for expensive ballast water treatment system. The key feature of ballast-free ship include ballast trunk V-shaped hulls, CFD optimized design, and twin propeller system that improve stability and propulsion efficiency. This slide is talking about LNG fuel for propulsion, TFDE. LNG fuel is used for propulsion to reduce emission and improve efficiency. TFDE system offer low maintenance benefit but require advanced electrical component. That is LNG fuel for auxiliary engine operation. LNG power auxiliary engine reduce emission and operating costs. The system operate in gas only, dual fuel or fuel only mode depending on fuel availability.
To reduce sulfur emission from ship exhaust, we use exhaust gas scrubber systems, either closed loop or open loop. Closed loop scrubbers use fresh water mixed with alkali to neutralize sulfur. The water is recirculated and discharge can be avoided with entirely optional holding tanks. Open loop scrubbers, on the other hand, use seawater directly and discharge the treated water back into the sea. They are simpler and require fewer components. Let's look at two important propulsion improvements. First, the advanced rudder and propeller system. By streamlining the design, we can cut fuel consumption by up to 4%. This not only reduces emission, but also helps the vessel achieve better speeds. Next, the speed nozzle, commonly used in tugs and supply vessels. It boosts propulsion power and improves efficiency. With this design, ships can save around 5% in energy consumption. Together, this innovation makes ships faster, more efficient, and more environmentally friendly. Let's look at two ways we can improve fuel efficiency and reduce emission on ships. First, hull paints plays a major role. By applying the right coatings, we reduce frictional resistance and save between 3 to 8% in fuel. Without anti-fouling coatings, fuel consumption could rise by up to 40%. Advanced options like silicon-based coatings create a smooth surface that prevents marine growth and keeps the hull clean. Next, the waste heat recovery system. This system captures heat from exhaust gases and uses it to generate steam. That steam can then be used to heat cargo areas, fuel oil, and accommodation spaces. With improved efficiency, this system can reduce fuel consumption by as much as 14%. Together, these technologies help ships operate more sustainably and cost effectively. Now let's look at two effective methods for reducing nitrogen oxide emission in marine engines. First, the exhaust gas recirculation system, or ERG. This system recirculates part of the exhaust gas back into the engine with scavenged air. By lowering the oxygen content and reducing the combustion temperature, it helps cut the nitrogen oxide emissions by up to 80%. Next, we have the water in fuel technique. By adding water just before fuel injection, the temperature inside the cylinder liner drops significantly. This leads to better combustion and can reduce nitrogen oxide emission by around 30 to 35%. Both systems are powerful tools for cleaner engine performance and meeting emission regulation. Let's explore two systems that help improve ship efficiency and reduce environmental impact. First, the improved pump and cooling water system. By optimizing the layout of pipes, coolers, and pumps, we reduce flow resistance. This leads to saving of up to 20% in electrical power and cuts fuel consumption by around 1.5%. Next, the sail and kite propulsion system. When used alongside conventional propulsion, this system harnesses wind power to reduce fuel usage and emission. It can lower nitrogen oxide, sulfur oxide, and carbon dioxide emissions by up to 35%, making it a strong step forward greener shipping. Let's look at two innovative propulsion technologies that support cleaner and more sustainable shipping. First, we have fuel cell and solar propulsion. Fuel cells use hydrogen to generate electricity without combustion, making them a clean and efficient alternative. Systems like PEM and molten carbonate fuel cells are already being explored for marine use. Solar propulsion, first used in 2008, helped reduce carbon dioxide emission and can generate to 40 kilowatts of power, a significant contribution to onboard energy needs. Next, the sandwich plate system, or SPS. This structure bonds two metal plates with a polyurethane core. eliminating the need for extra stiffening steel. It's lightweight, corrosion-resistant, and easy to install or reuse. SPS has been used in ships, bridges, and stadiums across 30 countries, and it's especially valuable for green ship recycling thanks to its durability and low maintenance. Together, these technologies represent a major step forward in sustainable marine engineering. These are the infographic summary for all the things that I've said before.